The world is just swimming in data. It can feel like a lot of random noise. But what if I told you that hidden inside all that chaos, you could find a simple, straight line that explains how two completely different things are connected? Well, that's the magic of linear modeling, and we're about to see exactly how it's done. So let's start with a kind of weird question. Can you actually figure out the temperature just by listening to a cricket chirp? It sounds a little nuts, right? But this is the perfect kind of puzzle that linear modeling loves to solve. We're going to use this cricket mystery to guide us through the whole process. Here's the game plan. First up, we're going to see how to take a boring list of numbers and turn it into a picture so we can actually spot a pattern. Then we'll figure out how to draw the one single line that best describes that pattern. After that, the fun part, using our line to make predictions. But, and this is a big but, we'll also talk about the crucial times when you shouldn't predict. And finally, we'll learn how to give our model a grade with one simple number. All right, let's get into it. Step 1. Before you can find any kind of pattern, you have to be able to see what you're working with. A spreadsheet full of numbers is it's just noise. To find that hidden signal, our very first move is to turn that data into a picture. And the tool for that job is the scatter plot. It's a really simple idea. For every pair of things we measure, say the number of cricket chirps in a minute and what the thermometer said at that exact moment, we put one little dot on a graph. Yeah, at first it's going to look like a random mess of dots, but as you add more and more points, something pretty cool starts to happen. A trend can literally emerge right out of the chaos. And when we're looking at that cloud of dots, we're usually looking for one of two things. On the left, you've got what's called a positive association. That's when the dots trend upwards, like the more hours you study, the higher your exam score tends to be. And on the right, you've got a negative association, where the dots trend downwards. Think about a car. The heavier it is, the lower its gas mileage. Okay, so once we've seen a trend, we want to nail it down. A cloud of dots is helpful, but a single, straight line, that's a powerful summary of the whole relationship. And we call this the line of best fit. So, how do we get this magical line? Well, there are kind of two ways. The first is what we call the eyeball method. You literally just look at the dots and sketch a line that looks about right. It's a decent start, but for the real deal, we use computers to do something called least squares regression. Now, don't get hung up on the fancy name. All it means is that the computer runs a calculation to find the one single line that is mathematically the closest to all the dots at once. It is the perfect fit. Let's jump back to our crickets. If we just eyeball a line through that data, we might come up with an equation that looks something like this. It's a pretty good guess, right? It basically says that temperature is about 1.2 times the number of chirps plus 30. Not bad for just sketching. But when we let the computer do the hard math for us, we get this much more precise formula. See how the numbers are just a little bit different? That's the power of regression. It takes our rough guess and turns it into the single most accurate description of the trend. This right here, this is our official model. Okay, so we've got a model, an equation. Big deal, right? Well, yeah, IS is a big deal because now we get to do the really cool stuff. We can use this equation to make educated guesses, to predict things we haven't even measured yet. Let's see how it works. We start with our model's equation. Then we ask a question, like, hey, if I hear a cricket chirping 30 times a minute, what's the temperature probably like? We just plug the number 30 into our equation where the C is, do the math, and out pops our answer, about 64.6 degrees Fahrenheit. We just predicted the temperature without even looking at a thermometer. Now, this feels like a superpower, but it comes with a really, really big warning label. Just because you have a model, it doesn't mean you can use it to predict absolutely everything. You've got to know the rules. First, there's what we call interpolation. This is when you're predicting something that falls inside the range of the data you started with. For our crickets, we measured chirps between 18 and 44 times a minute, so predicting for 30 chirps, that's interpolation. It's safe, it's reliable, you're on solid ground. But predicting a value outside of that original data range, that's called extrapolation. And this is where you need to be super careful. You're basically wandering into unknown territory and just assuming the pattern you found keeps going forever, which it almost never does. And there's a name for what happens when you push your model too far. It's called model breakdown. It's that point where the beautiful, simple relationship you discovered just stops working. It breaks. Our cricket model is a perfect example of this. The math might predict that at 40 degrees, the crickets would just chirp a little slower. But in the real world, nope. They stopped chirping completely below about 50 degrees. Reality changed, and our model broke down. It's no longer valid. So we've built a model, and we've learned about its limits. But that leaves one big question. Was the model even any good to begin with? How strong was that pattern we saw? Well, it turns out we can actually measure that strength and give our model a grade. And that grade is a number called the correlation coefficient, or just R for short. It's a score that always falls somewhere between -1 and +1. The closer R is to either 1 or -1, the tighter the fit and the better your model is. The closer it is to 0, the more of a random mess your data is. So, for instance, an R value of 0.95, that's like an A+. It tells you that your data points are packed incredibly tightly around a line that's sloping upwards. It's a super strong, positive relationship. And hey, negative numbers aren't a bad grade. An R of -0.89 is also a really strong A. The negative sign just tells us the line is sloping down. The points are still clustered really close to it. But an R value of 0, that's a total fail. It means there is no linear relationship at all. The dots are just a random cloud, and trying to draw a straight line through them is completely pointless. So, drumroll please, what grade did our Cricut model get? It got an R value of 0.9509. Wow. That is incredibly close to 1. It confirms what we saw with our eyes. The connection between Cricut chirps and temperature is a real and very, very strong pattern. Our model is fantastic, as long as we respect its limits, of course. So, there you have it. We started with a quirky question about crickets, and we ended up with a whole toolkit for making sense of the world. You now know how to see patterns in the noise, how to define them, and even how to grade them. So the only question left is, what hidden pattern are you going to investigate first?